Hi, my name is Sasha Malalou, and I have been working on a project called Computational Drug Design for COVID-19. I'm currently studying biology with a minor in chemistry, and I'm hoping to pursue a career in veterinary medicine. The overall goal for this project is to develop an inhibitor against Mpro. Mpro is the main protease enzyme of SARS-CoV-2, the virus that causes COVID-19. Mpro is a protease, which means that it takes really large proteins and chops them up into smaller proteins. The smaller proteins are key to the assembly and release of replicated viruses. So by inhibiting Mpro, we are essentially halting the viral life cycle and stopping the virus from replicating within your body. That's what makes Mpro a great drug target. The structure of this project has been entirely in silico, which means that all of our experiments have been done over the computer. That's because this project was started way back in June of 2020 when everything had to be remote. We've been using something called molecular docking, and we've been using a free software called AutoDocVina. And essentially how AutoDocVina works is you provide it with an inhibitor, you provide it with a crystal structure of Mpro from the PDB Protein Databank website, and it takes the inhibitor and puts it together with the protein and tests it in a number of different orientations called poses, and each pose is given a score. These docking scores represent binding affinity, so a higher binding affinity means that it would be a better potential drug. So that's kind of the overview of how docking works. The workflow of the project is we designed a number, over 200 different inhibitors based on previous research that we read about in literature. And we docked these inhibitors to a protein model of Mpro called 6YB7. Each of the different PDBs, protein Mpro structures from the Protein Databank website, have a different 4-letter/number code. The one that we were working with was 6YB7. So we gave 6YB7 and an inhibitor to AutoDocVina, and it tested a number of different poses and gave us a bunch of scores. And from these scores, we're able to see what parts of the inhibitors were the most successful and what parts were not, and use those findings to influence our redesign of inhibitors. And if we were continuing in this specific workflow, this purple side, that's exactly what we would do. However, upon more testing, we've realized that we cannot continue with the testing of inhibitors because we have to better understand our protein model first. Our protein model, Mpro, is incredibly flexible. This means that when an inhibitor or the natural substrate binds, the protein has to change or move significantly to accommodate that binding. So, as you can see in these structures here, the pink is apo, which means that there's nothing bound. The green is holo, which means that there is something bound. When something binds to the protein, it has to go from this position all the way to this position. This residue, alanine 191, moves 4.5 angstroms, which is a significant change in protein structure. This is telling us that this specific residue, alanine 191, or this residue over here, methionine 49, those are what we would consider flexible residues, which means they change significantly when an inhibitor or the natural substrate binds. Moving forward, before we can continue our docking of inhibitors, we need to identify all of the parts of the protein that are flexible and make sure that when we are docking to a structure of Mpro, all of those flexible residues are in the correct orientation, meaning they're out of the way of the inhibitor when it docks. Originally, when we were docking to 6YB7, we did not account for this flexibility, and that left a lot of the most flexible residues in the wrong positions, which led to kind of blocking of the docking, of the binding of the inhibitors. And that causes problems like what you see here, where the green, the docked inhibitor, didn't even make it to the correct location, which is seen by this inhibitor here, this pink one. So that's more of what we're focusing now on. We're trying to better understand the flexibility of our protein model before we can continue with docking studies. So that's a quick overview of the project. Thank you so much for watching, and that's all.